Hello everyone, welcome to this NPTEL course on Advanced Pre-Stressed Concrete Design. Now we are in the module on flexure. We will continue the discussion. And in this lecture, part 2, we are going to talk about the moment curvature behavior, which is a very important exercise for us to understand how different sections behave under flexure. Now, the expected learning outcomes after watching the video, the student should be able to obtain completely the moment curvature response using equivalent stress block. We will talk about what is an equivalent stress block, and the student should also be able to determine the moment curvature response for a flange section or for that matter any section using a concept called layer by layer analysis approach. Then the effect of various parameters, that is the effect of pre-stressing steel, the effect of non-pre-stressed tension steel and compression steel on the moment curvature behavior also the student should be able to understand. Now, let us first understand what is the significance of a moment curvature analysis. So, in moment curvature analysis, we do a sectional analysis. We take a cross section and we try to understand how that cross section is going to behave in flexure. So, these moment curvature, establishing these moment curvature curves are important because they become fundamental inputs for advanced analysis, like for earthquake engineering when we do pushover analysis or nonlinear dynamic analysis. You have to give the hinge properties, where the hinges will form and how those hinges will actually behave. To establish those hinge properties, the fundamental essence is to get the moment curvature response of the cross section, right. So, finally, for a pre-stress cross section, we are trying to get this kind of a behavior where we try to plot for a particular cross section how the moment and curvature is going to change. You can clearly see here for a pre-stress section, because even before any external loads are applied, we put pre-stressing. So, because of that, there is going to be a camber upward, right. So, the section will have some camber, that means the deflection will be on the upside and that will create a negative curvature. So, that is what you see here, right. So, that this portion is actually the initial curvature, that has to be taken into account. This is coming from the camber. Then when the external load starts applied, the curvature will become from negative to positive with increase in the amount of applied load or moment. Then you have yielding somewhere here and then you have ultimate. So, this is ultimate and this is somewhere you can say yielding, right, and you also have somewhere here cracking. So, these are the three important stages in the moment curvature behavior of a cross section. Now, again this becomes an input for plastic hinge analysis, and typically the rotation capacity of the section is calculated from the ultimate curvature, which is here. So, this is your phi u, and then you have the curvature corresponding to the plasticity, onset of plasticity, which is nothing but your yielding. So, this is phi p, and then the region over which the section is actually yielding, that is called plastic hinge length. So, when you multiply that, you kind of understand what is the rotation capacity of that particular region, right. So, it also helps establishing this moment curvature behavior for different cross sections, helps us to get the deflections through numerical integration of curvature, because you know from moment area theorem, right, the double integration of your curvature distribution will give me the displacement between the two regions where we are integrating, right. So, for example, if you take this kind of a beam, simply supported beam, let us say that I can discretize this beam into several segments of length delta x, then let us say that it is subjected to some kind of a uniformly distributed load. Let us say this is UDL, uniformly distributed. Then you know the moment distribution at different cross sections, right, along the length of the beam. Then for this beam again we know the cross section details, we are going to assume what is the steel from your design, right. So, for simply supported case, now I am going to have reinforcement somewhere in the bottom like this, right, because the tension will develop at the bottom. So, I am going to put steel on the bottom side, right. Now, if the reinforcement configuration does not change, then every cross section is going to be same. So, the moment curvature what I am going to get is also going to be same. So, if I know the moment distribution, I can also get the curvature distribution from this curve, right. So, this is your section property, this is your section property, right. So, if the section is going to be same, I am going to get curvatures along the length of the beam, right. Then once we have, so this is what we said, this is if at any point I know the moment mi, then for that I can get my curvature distribution phi. So, if I know the distribution of a curvature, we know that we can get your deflection at midspan by this simple integration scheme, right. Basically, you can get this integration from distributions of curvature and the distance of this curvature where it is located, right. So, in this way, for any given loading configuration, from the sectional analysis, I can also get the member level behavior. So, I can establish what is the relationship between the applied load versus deformation, right. So, the input becomes the moment curvature of the different sections that we have on the beam. Okay, now let us look at how do we analyze a rectangular cross section or how to get the moment curvature behavior. Now, I have taken a section with a width of b and depth of h, and your effective depth for the pre-stressing steel is small d, right. And what we are going to do here is, let us assume that I am going to have some strain on the compression side, epsilon c, right. And let us say that I am going to assume some neutral axis depth x, and once x is known, we can find out the strain at this point, which is called as, in pre-stressing we have two things. We have already discussed what is epsilon pi. Epsilon pi is your initial strain that what we are stretching the cable to, right. This delta epsilon p is the strain gradient from load or from the external load, I should say, right. So, this epsilon pi is already there. Again, you have a rubber band, you have stretched the rubber band to a certain strain. Now, due to external load, the rubber band is going to stretch further. So, that further stretching due to load is delta epsilon p, but the initial stretching is epsilon p. So, the total strain is going to be epsilon pi plus delta epsilon p, that is coming from external load, right. So, this is the strain distribution. So, similarly, we can we can calculate delta epsilon p easily. So, how do we get your delta epsilon p? From similar triangle, delta epsilon p by d minus x should be equal to epsilon c by x. So, from this similar triangle, I can get what is delta epsilon p for any value of epsilon c that I am assuming. Similarly, I can get epsilon pi is given to you already, right. So, epsilon pi plus delta epsilon p will give me epsilon p. So, this is the way we are going to calculate strains in the pre-stressing steel for any assumed value of compressive strain epsilon c at the top compression fiber. Now, again depending upon the epsilon c, my distribution of stresses are going to be like this, right. If epsilon c is greater than 0.002, then you will have this kind of a parabolic distribution. The stress at the bottom will be lesser, and somewhere here in the middle you will have f prime c, which is the maximum cylinder compressive strength, right. Now, depending upon what value of epsilon c that I am choosing at the top, the stress block is going to be different. If epsilon c is less than 0.001, then it will be triangular. If it is going to be 0.003, this will have this kind of a parabolic shape, right. So, depending upon the strain that I am assuming at the top fiber, my stress distribution is going to be different. Initially, it will be for small values, it will be triangular, then it will become peak value, then it will become a descending parabolic curve. So, it is going to be varying as a function of my epsilon c. Now, to integrate this to get compression force is difficult for me. So, Whitney came up with a very elegant approach for converting this different stress block into an equivalent rectangular block, because for me area of calculating this rectangular block is easy. So, he defined the maximum stress is going to be alpha 1 into f prime c, and the depth of this block is going to be equal to beta 1 into x, where x is your neutral axis depth. Now, we know that this C is going to be alpha 1 f prime c beta 1 into x. Let us say if it is a rectangular section, then I have to multiply with width. So, this is going to be your compression force, right. And because it is a rectangular block, I also know what distance it is acting c from the top. So, this is going to be beta 1 x by 2, this is the distance. So, d is nothing but a is equal to beta 1 x by 2. So, this distance is going to be d minus a by 2. So, now our criteria is to somehow come up with parameters for alpha 1 and beta 1 as a function of strain that I am assuming, strain profile that I am assuming, or epsilon c that what I am fixing at the top fiber, right. So, these parameters alpha 1 comma beta 1 can be obtained by equality of resultant forces and the resultant location for any given strain epsilon c. So, the moment you give me epsilon c for the assumed stress strain curve, I can calculate alpha 1 and beta 1. Now, how to do that? So, that is what we are going to look at. For concrete, we are going to use equivalent rectangular stress block parameters, which are alpha 1 comma beta 1 that we discussed. The first criteria should be the resultant forces from either it is triangular or parabolic or descending parabola, whether that equivalent force plus the rectangular stress block force should be same. So, how do we do that? So, this is what we have. For example, here I am considering epsilon c to be, let us say, greater than, let us say 0.002. Okay. So, then only you will have the descending portion, right. This area I want to equate it to this rectangular block, right. So, the CC from the actual stress block and CC from rectangular block, they have to be same. That is the first condition, the resultant forces should be same. So, if you do simple integration, for example, let us say this, if I take a small strip like this, right, the strip, let us say that the thickness that I am going to take it as dy, and the strip is at a distance y from the neutral axis. So, I do the integration. So, the force for this strip is going to be Fc into B into dy, because we are talking about a rectangular section. So, B into dy and Fc will give me the stress in this small strip. Now, I integrate it from 0 to the neutral axis depth x, then it will give me the entire force that is there in the parabolic stress profile that what we have assumed. Then that should be equal to alpha 1 f prime c into beta 1 x, this is the area of the rectangular block, multiplied by B, which is the across the width that it is acting the stress block. So, the force will be the area of the stress block multiplied by the width of the cross section, right. So, you get this. So, this is the condition number 1. Now, this Fc is function of your epsilon c, right. So, the stress is actually function of your epsilon c. So, somehow using these provisions, we know we have also assumed a strain, right. At x distance, my strain at the top is epsilon c. At y distance, what would be the strain? So, the stress can be expressed in function of epsilon c, right. So, we can do that. So, we know the relationship, we are going to use this parabolic stress block, stress strain curve. Okay. So, in this first part of the module, we are going to use only parabolic stress strain curve. Okay. Different people have different stress strain curve equations. One for typically for concrete strength less than 40 megapascal, this parabolic model seems to be closely predicting the actual response measured in the experimental testing. But if you go for high strength concrete or special concrete, of course, this relationship may not be valid. So, here we are explaining the procedure for getting alpha 1 and beta 1 if I assume the parabolic stress strain curve model, right. So, when you do this equivalent the analysis and then try to find expressions for alpha 1 and beta 1 in terms of epsilon c and epsilon prime, because f c can be expressed in terms of epsilon c. Similarly, this can be expressed, y can be expressed again in terms of epsilon c. So, if you do all these things, you can find an expression relating alpha 1 beta 1 to epsilon c and epsilon prime c like that. And you know that epsilon prime c we take equal to 0.002 for f prime c less than 40 megapascal. So, you know that, right. So, we get that. So, then we find one equation for alpha 1 in terms of epsilon c and epsilon prime c like that. Now, I have two variables which is alpha 1 and beta 1. So, I need to have one more conditions, then only I can solve for them, right. You have two variables, you need two equations to solve them, right. So, from here we know that C c is again we have already explained that, which is alpha 1 f prime c beta 1 x into b. Now, what is the second condition? So, whatever this location of your C c should also be same, right. So, the C c magnitude should be same and also the location of C c should be, then only they will be equivalent, right. So, now for example, if this block you see when you integrate, you know that it is going to be at a distance, some distance, let us say y bar from the neutral axis, right. Now, here in this case rectangular block, we know that the location of your C c is at a distance of a by 2. So, we can say that this centroid is this y bar in this case is going to be neutral axis depth minus a by 2, which is nothing but beta 1 x by 2, right. So, this y bar from 1 and this y bar should be same, the 1 and 2 should be equal, right. So, that is what we are writing. So, this y bar, if you do the integration of the force, we know that centroid can be calculated by the force multiplied by the distance y, right. So, you integrate that for each force for the strip and then you take the moment of that force, then divide by the force, you will get the centroid of the location of your C c. That should be equal to x minus beta 1 x by 2. So, now y can be expressed in terms of epsilon c and everything can be converted in the form of epsilon c. So, when you do that and you do the simplification, you can get another expression for beta 1, which is 4 minus epsilon c by epsilon prime c divided by 6 minus 2 into epsilon c by epsilon prime c. Now, you see we got two equations. So, this is beta 1 is there, the first one related alpha beta 1 to epsilon c by epsilon prime c. Now, first I calculate beta 1, then from the first equation I plug in the value for beta 1 and get the value for alpha 1. So, for any given strain epsilon c, I can find alpha 1 and beta 1. The moment I get alpha 1 and beta 1, I can calculate my C c and I can also calculate the location of my C c. Okay. So, now let us see how the compatibility condition. So, this is to integrating the compression force or the compression stress profile, we have difficulty. So, we found a shortcut to do it in a simpler way using equivalent rectangular stress block parameters. Now, let us see how do we, because to ensure force equilibrium C c equal to compression force in concrete is equal to tension force in steel, we need to calculate C c, that is why we did that. Using strain compatibility, again strain compatibility comes from the first part of the lecture that we discussed, plane sections remain plane before and after bending, that gives me that strain variation is going to be linear, right. So, for a non-pre-stressed steel section, we know that the strain in the steel is always equal to the strain in the surrounding concrete, right. So, this epsilon c is a strain in the concrete at the level of steel, epsilon s is a strain in the non-pre-stressed steel, and here in pre-stressed steel we have seen that epsilon p is nothing but epsilon c plus epsilon pa. Now, the epsilon c I will tell you what it is. We have that is coming from the initial strain because of the application of a pre-stress. Now, let us see what is that. You see here the strain difference epsilon pi is the initial strain in the pre-stressing tendons when the concrete at that location has a 0 strain. That means epsilon c is 0, then you have, but sometimes due to the application of pre-stress, epsilon c will not be always 0, right. So, a difference in strain occurs when the strain due to the external tensile axial load balances the compressive strain due to pre-stress. So, that means let us say when I apply some load due to tension, that epsilon c initial strain, compressive strain will become 0. So, that whatever the difference at that instant is what we call that as delta epsilon p, which is the strain difference in the tendons with the, or I should say epsilon pi is the strain difference in the tendons with the adjacent concrete. Now, you can see epsilon pi now can be related as epsilon p minus epsilon c. That means, it is an effective strain what is there at service minus the strain in the concrete which is applied due to the pre-stress. So, if you know the amount of pre-stress, you can calculate, but typically this epsilon c value will be very small, but sometimes we ignore them, but depending upon the condition, for example, epsilon c will be equal to 0 when you have pre-tension system. In post-tension system, it may need not be 0, so you have to calculate, but this value is going to be very low, right. So, now let us look at the constitutive model. So, this is the strain difference. So, again I have said we are going to use the parabolic model, Hognestad parabolic model. Usually it is valid actually up to 40 megapascal, and for pre-stressing steel, we are going to use this idealized bilinear curve we explained in the material chapter module. You can go back and look at how to get these values. So, this is EP, the elastic modulus for pre-stressing steel. We are going to assume 195 gigapascal, and we have discussed that when you do this production of your high strength pre-stressing steel, the elastic modulus slightly reduces. So, we are taking, instead of 200,000, we are taking 195,000. And you can see here in the bilinear curve, you get yielding, this is epsilon py happens at 0.0083, very high strain compared to that of non-pre-stressed steels, and the yield stress FPy is taken as 1618 megapascal, and this is your ultimate strength, which is equal to FPU, which is equal to 1860 megapascal, and at this strain 0.002, the strand will rupture when I do the the tension test. After that, the stress is going to go back to 0. This is the constitutive equation we are going to assume for pre-stressing steel in subsequent slides. Okay. Now, what are the stress strain curve that I need to assume for non-pre-stressed steel or a deformed steel which is not pre-stressed, and this also we call that as a passive reinforcement, because so pre-stressing steel is also called as active reinforcement, because even before you apply any external load, pre-stressing is already having some stretching. That is the reason we call that as an active reinforcement, because it is always there is some strain, but for non-pre-stressed steel it will be at 0 when external loads are not there, right. So, and we are going to assume this. So, basically we are going to take this ES equal to 200 gigapascal, and this is your yield stress, which Fy equal to 415, and this is your ultimate strength. Again you can see here I am taking it at strain of 0.05. So, pre-stressing as a non-pre-stressed steel can go up to 0.05 strain and it reaches its ultimate. So, pre-stressing steel is having lower ultimate strain compared to that of non-pre-stressed steel, that you have to keep in mind, because it is going to fail at a lower strain. So, we need to be careful. Okay. Now, let us look at how do we do the moment curvature analysis. Like I said, when I keep varying the strain distribution, I am varying the strain in the concrete of different magnitudes. For different values of epsilon c, we assume different values of neutral axis depth and choose the value of x that gives me the satisfy the equilibrium condition. Then you can calculate compression force, tension force, and then you can take the moment of these forces to get moment resistance. And we have seen that the curvature is nothing but epsilon c divided by the neutral axis depth for any value. So, we have assumed epsilon c, then for the iterated x value that satisfies the equilibrium condition, once we get that, we can get the curvature. So, now let us say see from cross section analysis. This is a very simple pre-stress cross section with a pre-stressing steel AP at a distance of d, and you can see here if I assume, so this is assumed, right, this is assumed for an assumed value of epsilon c, and for x is assumed. So, you know the strain distribution. Once epsilon c is assumed and x is assumed, then you know what is the strain distribution, right. So, from this similar triangle, now I can get delta epsilon p, because I know this is given, okay, this is given, right. Typically for epsilon pi is given, because again how is this given? FPI, I told you, typically we take it as 0.75 times of your FPK, right. So, epsilon pi is going to be 0.75 times FPK divided by EP. So, using your stress strain curve equation. So, this is what we are going to do. Now, so the first step to get moment curvature is, now I am going to use assume some epsilon c value. So, what we are going to do, these are the epsilon c values. So, I take epsilon c1, epsilon c2, epsilon c3 like this. So, I take different values along the stress strain. So, always the strain values will be incremented to a higher value, okay. So, like that we do. First we choose epsilon c, right. The once epsilon c is done, then what we do is I can calculate alpha and beta, which are your equivalent stress block parameters. We have derived the equations previously, and once you know alpha and beta, and for a given value of x, then I have to assume x also, okay. So, this also I assume. So, but I have to iterate in such a way that compression and tension force should be in equilibrium, right. So, calculate C and T in terms of x, the assumed value of neutral axis depth, then solve for x using C is equal to T, which is your equilibrium. This is your equilibrium condition, right. This is equilibrium condition. So, once this is done and x is you have iterated to the x value to the level that equilibrium is satisfied, then you can calculate your epsilon p. Once epsilon p is basically epsilon pi plus delta epsilon t, we have seen that. Then we have to see whether epsilon p is less than yield or not. If it is less than yield, we know that the stress Fp is going to be Ep times epsilon t, right, just a linear relationship. Otherwise, I have to use the bilinear curve. We get into the bilinear curve, the slope here it will not be Ep, some fraction, otherwise the Fp have to be, I have to calculate that as Fpy plus some delta Fp. So, that we have to calculate using the bilinear curve. So, this is using bilinear curve, okay, that from IRC, okay. Okay. So, then everything, if it is less, then we get your let us say if it is less, in this case, then I can quickly calculate my momented curvature, right. If it is not, then you have to use it. This also, then again equilibrium has to be satisfied. So, you have to check, right. And now Fp is going to be 16. So, this is your Fpy that we have discussed plus delta Fp. If it is no, then it is delta Fp. Then I have to recalculate your x, and then I have to calculate my moments. So, this is, if it is less, then I can just simply do the linear, right. Otherwise, the Fp is going to be higher value, it is not going to be linear, then I have to recalculate my x and my equilibrium condition will not be satisfied. So, you have to calculate Ix in a iterative way, okay.